Hello, my name is Rachel Zhang, and this is Lab 1 Constant Velocity. So as an introduction, the purpose of this lab is to analyze the position of an object traveling at a constant velocity, and then we want to compare the object's observed motion to the object's predicted motion calculated by a model. In this case, we're using Tracker and GlowScript. So just a brief overview, the object in motion is a glider, which is the system, and it's moving on a linear air track, which is the surroundings. And we're going to be using Newton's second law to do our calculations, and a brief preview of our results. If there is no force acting on the glider, then the glider should be moving at a constant speed with no change in direction. Newton's second law states that the acceleration of an object is directly proportional to the net external force applied, and it is indirectly proportional to its mass. So this gives us the equation F net is equal to the change in p over the change in time, and you can derive the velocity update formula, which is v final is equal to v initial plus the net force times the change in time. And this basically tells us that if the net force acting on the object is 0, then the velocity does not change at all. So these are our lab steps. So the first step is to record a video of the glider sliding across the linear air track. And then the second step is to input this video into Tracker in order to collect data on the object's position at different times. And then we are going to use GlowScript to create a computational model of the object's motion versus its time, and then we're going to compare the object's observed and predicted data in a spreadsheet utilizing a graph. So this is the video of my object sliding in Tracker. So I marked every point on the center of the glider sliding across the linear air track, and on the right side you can see the time versus the position, and also the graph of the time versus the position. So these are the Tracker computations. The total time is the final time minus the initial time, which is 2.3 seconds. The initial position is given by the first x coordinate, and then the initial velocity can be taken by taking the change in position from the first two time frames divided by the change in time, and this gives us our initial velocity. And for our GlowScript inputs, the first thing that I changed for the code was the net force, and I made this to be 0, and then the initial position and the velocity as we calculated before. Because the video was in 30 frames per second, I changed the delta t to 1 over 30, and since mass has no effect on the velocity, it basically cancels out. And then I updated the velocity to include the position formula. And here are the results from GlowScript, this graph. It looks pretty similar to the Tracker graph as well. So here is the Tracker versus GlowScript data in an actual graph together, and as you can see, the Tracker graph actually deviates from the GlowScript predicted graph. And there are a few reasons for this, including human error, so I may have not clicked directly in the center of the object when I was tracking it on Tracker, or maybe the video was unclear or had like an angle to it which could have messed up the tracking. There could have also been number precision errors, so rounding and calculations may have affected that. And the third thing, which is probably the largest factor, is outside forces such as air resistance or friction and other miscellaneous forces. These could have caused the glider to slow down because it's being pushed back by different forces in the surroundings, and this could have caused the deviation from the computational model. So the additional questions: what if the axes were interchanged? In this case, the slope of the graph would be positive. Since it was originally negative, it just flips the slope. And is the net force in this case actually 0? And if it is it possible for you to say how many pushes and pulls were added together? So because the model's actual graph wasn't exactly the same as the computational graph. The net force wasn't actually 0, and this could have been due to other forces or errors. However, we know that in the y direction that the net forces are actually 0, otherwise the ball could have been moving straight toward the ceiling or into the ground. Thank you.